The plan is we're going to work through a series of different steps today. So the first talk today is going to give a little bit about missing data. So we're going to sort of bridge from the data collection yesterday and think about the distinction between what the data you miss and the data you have. And then we're going to move on to some sort of it's a really high level overview of what network regression models kind of look like and what the classes of those models are, just to get you sort of seed in the back of your head. And then we're going to work through a series of, I think Craig should be here any minute if he's not here yet. He'll talk about a certain kind of model, which is known as the peer influence model, sort of theoretically. And then we're going to jump into some more statistical sort of bits. And then Tom Valente is giving us some work on interventions. And then we'll do some work on visualization and so forth. So it's a pretty packed day. I think I'm forgetting somebody on the schedule. So yeah, and Scott Duxbury. So we'll start with the first set of models. Thank you. That's what I remember. The first set of models are cross-sectional, and the second set of models are dynamic. So you'll get a sense of what all those are. That's I want to be that's a lot, right? And I appreciate that. So this is when I had that little picture of the fire hose. Today is that day. All right. So don't worry. It's just hold on tight. You'll be fine. And all the slides are there, and you can go through it. The key, like I said, of the first day is to try to understand the process and the reasoning and this kind of stuff, right? A bit of basic housekeeping. Tonight we have a barbecue down on the deck, so if you're up for that, please swing by. If you wanted a non-pork-centric meal, let me know. If you hadn't, let me know. We've ordered a few of them from Pure Soul for everybody that says local. They're a great vegan. They're probably the best vegan place in town. So if you're interested in that, let us know and we can make sure that happens. Otherwise, it's just there's going to be beer and barbecue on the deck. So hope you can join us. There'll also be not beer if you don't want. So that's the plan. All right, let's jump in. I guess no time like the present. So one of the key elements, the program kind of had it backwards. We're going to focus, the main focus of this talk is going to be on missing data. And this is a set of work that John Morgan, myself, and Jeff Smith, I don't think John's quite here yet this morning, the three of us have been working on in a series of papers that Tom was kind enough to let us publish in Social Networks with Roman numerals, which was always one of my goals as a scholar, was to have Roman numeral papers. And so I think Ashton beat me. He has a 5 on one of his papers, which is pretty good. So we made it to 3, and then we're sort of shifting gears a bit. But there was this intuition coming out of the early work in social networks, particularly the work in anthropology, that these are system measures and that any missing data was going to destroy your inference and you weren't going to do anything. And the question was, well, how bad are we? Because we never really get a full sample, right? So we know that even under the best of circumstances, we end up with missing data. So if that's the case, should we just pack up and go home, or do we have a hope that we're going to get something good out of this? And so the short answer is, it ain't nearly as bad as you think it is, and it turns out we can know a lot from it. So we're going to talk through, first conceptually, how missing data is generated and the ways that we think about it, and then some sort of just basic logical reasons about what it means for your inference, and then we're going to talk about sort of our finding from a set of Monte Carlo findings and what to do about it. So the basic idea is that if this is your real world out there in the population, you go out and sample what you can and try to get everyone to take your survey. A few people refuse. And so the data you end up getting, like in this little example, all the red people just didn't take the survey. The data you get is a sample of the data you wanted. So it's never a full representation. Now it turns out that there's lots of different flavors of missing data. You can be either missing data on nodes or you can be missing data on edges. We're going to focus on the missing data that comes from the nodes being missing. So we assume that when nodes are missing, when people refuse to take your survey or otherwise don't want to be part of your study, whoa, what was that? Should not have automatically moved. When that sort of type of thing happens, you end up with all of their edges are gone as well. It can also be the case, of course, that people just don't remember to answer or don't name people. So even there, you can have missing data within ties, but I'm going to ignore that for today. So what does missing data look like? From a very practical standpoint, when you go out and give someone a survey, and this is what the data looks like from your respondent's point of view, there's lots of different ways that you can generate missing data. Probably the most common way is that people nominate others in the network that you don't have any information about, right? And so these are the people that they nominated that either weren't on your roster, was a name you couldn't match, or refused to take part in your survey. And in that case, what happens is when multiple people nominate this person, you as a respondent, when you see them, you can't tell that they're the same person. So you often get this, not is it just that the data is missing, but the information you get about those others that are outside, like some proportion of them are going to be conflated, and you have to treat them as if they're separate. So the most common, like this is the most commonly comes out of survey features, where you end up with some kind of roster or something. And for example, in Ad Health, we had to build the rosters in the summer, and kids would move in September before we gave the survey. So there's all kinds of kids who were in the room who weren't on the roster, and so when they get nominated, you couldn't know if they were the right person or not. So they're unmatched. That's what the UN stands for. Same thing, of course, happens to people who are outside of your boundary. So remember, network analysis assumes that there's some kind of a boundary specification, often a school or a company or a hospital or something like this. When that happens, again, if I nominate someone outside the boundary, we can't know if that person is the same person or not. There is one solution for this, which is to collect some kind of minimally identifying information so that you can do some kind of smart matching. So it's not unreasonable to ask the gender, for example, and race and age, and things that will help you say, well, I know these two people are different, and it's possible that these two people are the same, and you can play some games about figuring out how much that distorts your measures. Now, oftentimes, when you have these kinds of features, right, you'll end up with data that is like, this is the same picture just from a different point of view, where the person, the focal person in this case, is not on the roster at all. You can have people who name others, but they can't be named in return. And this non-roster problem really creates an issue of asymmetry in your data. So you'll end up with lots of people who get nominated who are receiving ties who couldn't nominate ties because they didn't fill out the survey. But you also then get people who filled out your survey, but they couldn't be nominated in return. And so you have to make some assumptions about what proportion of those ties are reciprocated. As a very practical matter, when you do these kinds of models, what I recommend doing is when you get your data, you're going to have a set of edges, and I'll show you right here. When you collect your data, there's always going to be some set of nodes for which you have all of the information. So these are all the relations amongst the people who are on the roster and nameable, right? And so that's your minimal set, your minimal coverage set. So you know all the relations amongst that realized boundary. And so it's good to take that data and treat it as one set of models. But then you can also just assume that all the rest of your data is there as well. And so it's a little frustrating with colleagues that I work with. Whenever they send me data and say, construct measures for me, I'll end up creating like 7 different measures for each, 7 different versions of each measure, because you're going to have the minimal set amongst just ties. You're going to have the maximal set for the ties that include all those out bits. But you have to understand which kinds of measures are good for each of those. And so if you're really interested in reciprocity, then you really the only good thing you can do is focus on the ties within the set that you have full information on. If you're interested in things like global centrality or centralization, then the full network might be better because you have a better coverage of what's there, right? And so thinking about how your data matches your problem is really important. Now, what these next set of slides are designed to show is this logic of what information you have when you have a design-based sampling strategy. So such as many of these partial network analysis sort of strategies, in which you start with usually a seed of some sort, or some set of seeds, or some set of people who are willing to take your coupons in an RDS, and you interview all of those folks, and then they recruit others, or you go out and you recruit the people they've named. When that happens, you end up with this wave structure. And the beauty of this kind of wave structure is you actually have a lot of information about people that you might not think that you have. So you obviously have all the information amongst the people who filled out your survey, but you also have all the null relations between the people who didn't fill out your survey or the people who filled out your survey and the new people connected. That is, the people like in sort of this ring of the set. Because if there was a tie there, presumably your focal actors would have named them, right? So in some sense, the zeros here The non-tie from this person to this person is real, because if it were there, they had the opportunity to name that person and they didn't. And so the whole point of this slide and the next few that are on this piece is to help you think through this logic of who's in the risk set for your model. So there's a risk set that's the true risk set, which is the people who could be named and are within your boundary. And then there's the risk set that was realized by virtue of your sample design. In many cases, your risk set gets constrained. And so in this case, there are people out here 3 steps later, and we can't know anything about them because these folks weren't allowed to survey anybody. They weren't allowed to name anyone. So whenever you stop the connection, you're not there. Now, if you have a model where you don't let your second step folks name anyone, so like I name a peer, I interview those peers and they tell me who's there, that means that I don't have any idea about the relations amongst these set, right? So they're now out of the risk set because these folks had no opportunity to name within their set. And you can think about this, a classic RDS, you get no transverse edges, right? So in that kind of a model, you start with one node, you contact the people they name, they contact the people they name, and so forth, and you snowball out, but you never get these cross-tie edges. And this is why the network sampling with memory idea that Ashton told us about a couple of days ago is so powerful, because you get those kinds of transverse edges, and once you have those transverse edges, you can make some inferences about the probability of closing triads in your set. So it's a nice feature to have. But it's expensive. You have to go and interview those people and ask them about their questions, and so that's always the trade-off. This is the same kind of idea, just displayed a little differently, so I'm not going to go through what's there. So again, those particular slides were specific to this notion of a snowball sample or something like a snowball sample, and your problem is probably going to be different. But think about how your system has constrained who can be named. So when we go into school, the Prosper data, for example, all of those relations are within grade. As Jimmy was saying a couple days ago, a grade is a weird boundary in a school. And so we know there are ties outside of the grade, and we probably ask kids how many friends they have outside of their grade, but we don't know exactly who they are. So that's a sample design constraint on missing data. And design constraints on missing data are going to lead to these kind of logical holes that then constrain the kind of measures you can have. So what we wanted to do, I don't know why this thing is moving automatically. There we go. There must be some timings built into this presentation that I forgot about somewhere. All right. One might assume that by this point in my career I know how to use PowerPoint, but there you go. Given the fact that the one way to read all of these examples is that you're going to have distorted data. So what do we do about it, and how does that affect what we're playing with? And so as you probably got a flavor, a sense for the other day, when I don't know the answer to something, I simulate it. I make it up and then try to figure out what I could learn from that data. That's my basic rubric for how to do work. And so this is what John and Jeff and I worked on. We thought, well, let's just take a set of data and figure out if we induce missing data in it, what do we recover when we measure it, when we model it as if we didn't have missing data? Like how much error is actually introduced? So we start with a set of networks that we're going to treat as if they're complete, as if they're true. Then we're going to remove the nodes, and we have a whole series of different strategies for removing them. First, we're going to do the obvious thing that's done in all the sort of standard missing data literature, which is to assume missing at random. That's sort of your best hope. So if the world is missing at random, what happens? Then we're going to be a little more realistic and say, let's assume that missing data is driven by either peripheral nodes who aren't engaged and they quit, or central nodes who are too busy. So either of those things could be a possibility, and we'll ask about that. Then we're going to ask, what happens when you apply various kinds of imputation strategies? So if we know that our data is missing in one way, can we recover it nicely, and will that help? And what does that do to the measures that we do? And of course, you do this many times, and you end up with a solution. So there are lots of different. We wanted this to be it's a weird kind of set of papers, because we wanted these to be reference papers. These are papers that you're supposed to go to when you're doing your study and go, I got a paper that looks like Smith, Moody, and Morgan's network number 6. And so my result is probably like theirs. That's what we had in mind with this paper, which is why, again, I'm thankful to Tom for letting us publish it, because it's got these ridiculous figures you're going to see in a second. So what we just tried to do is pick lots of different kinds of networks that we think would represent the kinds of networks that sociologists and health researchers would use. And so we have 12 different networks that range in size from the smallest is 43, and this is a corporate interlock network. And what's nice about this network, right, is that it's really clear. You can just look right at it and see what's there. And so it's got a nice core periphery structure. There's some isolates and pendants, but because it's small, it's really easy to see what's there. It's a corporate interlock network, so it's actually a one-mode projection of a two-mode network, but the two modes are sparse, so it doesn't have a lot of cliquing in it, so that's kind of nice. The prison network is a classic data that was collected in the 50s or 60s, if I remember correctly. And this was all social relations inside of a prison, and so it has a nice sort of little clique structure up here and a little bit of division. Then we get into some bigger networks. I guess the sorority network is fairly small, but you get into something like the social networks co-citation network. What's nice about this is that there's different subfields in the discipline, and so you get these bigger clusters. And then we have a more dense 6th grade network. In this case, this is 6th graders, right? So it's probably no surprise you have boys and girls, and so because they think each other are icky at this point. Revusitter Elite, this is data that Ben Cornwell and Lisa Keister collected in a large Midwestern city, asking people to do just a classic elite study. So it was a nomination of people who were like you and who you think are elite in the city. So it has this really nice centralized feature to it. We have a set of other high school networks and larger scale networks. And sort of one of these is the Prosper School. One of them is built off the Ad Health Network. This is a corporate exchange network, and then we have a couple other sort of big, weirdly shaped networks. So the thing that's nice about the Colorado Springs network is it's highly centralized, but it's not centralized in a pure core periphery. There's lots of different stars in the network, and so that's what we took that. So we have these 12 different networks. And then for each one, we want to go through and ask we want to construct a series of measures with and without missing data. And so we have a series of measures that have to do with the kind of metrics we talked about the other day. So we have centrality and centralization scores, and then we have a series of topology scores. And so this is things like the bicomponent size or the component size, and then things like just simple closeness centrality and so forth. The Concore result is I'll explain what I mean in a second. So now, I do this to myself, right? And so ask yourself, you have now 12 networks, and you have, I don't know, something like 18 different measures, and then you have a dozen different levels of missing data. How do you explain to people what you found, right? And so this is what we came up with, and you can tell us if this is sensible to you or not. But our logic was that we know the cardinal values are going to be wrong. If I delete 10% of the ties in the network, then on average the density is going to, the number of ties is going to be 10% smaller. So the cardinal value is going to be wrong. But in a regression context, we don't really care about the cardinal values. We care about the correlation of the measure with other things. And so the question is, how good a proxy is the measure you observe to the true measure? And so we just created a correlation score. So in this top line, that says that the true value, before we induced any missing data, and we correlated that with the observed value when you have missing data. And then if we remove 10% of the nodes, you end up with this correlation. If you remove 70% of the nodes, you end up with this correlation. So that gets flipped over here on this side. And so on this side, what you see is the percent missing on the x-axis, and that correlation score is on the y-axis. And so what you see here is that at 10% missing, your correlation to the true value is well over 90%. So if you have a little bit of missing data for in degree and a network that looks like the River City elites, it doesn't hurt you at all. You can go all the way out to 70%, and you end up with the mean missing value of still over 90%. Right? So your correlation is 0.9, even if you're missing 70% of the nodes for this case. Now that's a really good case, right? And so I showed you this one for a reason, because it sort of tells my story nicely. But that's what all of these plots look like. And so you're going to see a fair number of them, as you might imagine, for all the rest. There you go. So these are the results across all of the different models. And so just to, again, have the first thing to do is to step back and sort of ask yourself, what's the big picture story I'm seeing here? So the big picture story is across all settings, across all networks, there's a negative slope. Well, that's obvious. That's what we expect. That the more missing data you have, the worse your measures, the worse your calculated measures are going to be proxies of the true measure. But the slope of those measures really differ across the network. So there's high variability across the different kinds of networks and the different kinds of measures. So for example, if I'm a relatively small, sparse network, and I'm looking at something like Bonasich power centrality, there's a strong linear association between the amount of missing data and the realized score. The amount of the drop in the correlation is going to be 7% for each additional 10% of data missing. So that's what that slope score is here. And so I think that on the one hand, and this is all random missing data, the first story that comes out is that size helps. So small networks, right, tend to have the strongest drop in overall centrality, with the exception of a couple of the slightly bigger and more sensitive measures. The other sort of quick sort of take-home bit is that in degree and out degree are really robust measures. That probably shouldn't surprise us because these are local measures, right? So the number of people who nominate me or the number of people who you nominate, a random sample of those people are good representatives of it. And I think what people don't appreciate is that they're good representatives up to, we're talking 60, 70% of missing data, you're still getting correlations above 0.8, right? And you get down to the real system level measures down here. So these ones really do great. The system level measures are where my centrality depends on someone else's centrality, which is eigenvector of Bonasich centrality or closeness in between a centrality. These can be pretty sensitive. And so it really does depend on the kind of network you have. Highly clustered big networks like co-citation networks or co-authorship networks or the River City elites, these tend to be reasonably robust to these features. But very spindly networks or highly transitive networks like the school networks or the Colorado Springs networks or the other sorts of Prosper networks, these things tend to have a very strong relation. They degrade quickly with respect to missing data. So for example, if you look at the elite study here and between a centrality, it ends up having a pretty huge effect. Now, we don't expect you to go to these plots and go look at it. So there's another way of displaying this in a minute, and I'll show you that. These methods are the exact same kind of story, but you'll notice that the, the plot here is like really different. So what are you looking at? This is a homophily coefficient. So you might imagine that one of the measures we really care about is the association of my characteristics with your characteristics. And that was the homophily score that we calculated. And we did the same trick. We said, let's look at the missing data and look at the variance and the resulting answer that we came from. And if you have a sortativity on in and out degree, you get this, essentially you get an unbiased estimate. That's what's happening in the middle, but the variance goes through the roof. All right, and at the far end, you might get some bias. That's what's coming up here in the mean levels. But oftentimes, these things are largely symmetric, especially once you get into larger networks, where you end up with a score that is an accurate estimate, but a giant standard error, right? And so you're going to be highly uncertain to what you get. For behavior, on the other hand, right, it turns out that homophily scores on behavior are really robust to sampling. So missing data on the network do almost no damage to homophily scores. And this is the hidden story in this paper, is that if your data are missing at random and you're really interested in whether or not peers smoke together or drink together or these kinds of behaviors, it doesn't matter sort of even if it's a weak association, you end up with an unbiased estimate across the board. And not even terribly like variable responses. Because remember, we're looking over here at 70% missing data at the end of these, and you're still not an unreasonable estimate on these sets. So that's good news for applied analysts who care about homophily, which is, I think, probably the bread and butter of most of us in the health world, that your networks are not really being destroyed too much in terms of missing data. Now, the final sort of set of scores are what we refer to topology scores. So this is the shape of the overall shape of the network you're going to induce by looking at by this kind of missing data. the story is sort of a mix here. It does a little bit better. We had to add some positive sort of branches to this. By and large, it's much like the centrality, so the individual level centrality scores. There's a negative correlation, so it degrades over time. But it's because of a few of the small networks, these ones that this is not my favorite display, as you can tell. But the take-home story is that the hierarchical mixing scores tend to do the worst, and the proportion of the nodes in the biconnected component and distance scores tend to do the worst. And it makes sense when you stop and think about what this is. These are scores that depend on the long distance path structure of the network. And so if your score depends, if your topology is being calculated on the long distance path structure of the network, it's a little more sensitive than it would be with something which is effectively the aggregation of a local score, which would be the transitivity score or the hierarchical tau score. So the concore, the role sort of division, and this is, we say we just take the network and cut it at 2 steps each time. Those end up being very stable. So if you want to do block modeling in these networks, because block modeling tends to be the aggregation of local orbits, it does pretty well. So even though you end up with a fair amount of missing data, it doesn't destroy the thing overall. I'm really sorry there's no coffee. I mean, I'm putting myself to sleep here. So, all right. So you don't have to go to these charts to go figure out what you're doing. We have these wonderful little lookup tables in the papers. This is taken from the second paper where we did the same exercise, but we made the missing data correlated with centrality. And what these tables do is they allow you to go here and say what's the most missing data that I could get in this network and still end up with a 0.9 correlation between my observed score and the true score. And so if you're looking at something like, if your network is like the sorority network, sort of an open, not very dense but small network, you could miss something like 23% of the missing data, and still you could be missing almost a quarter of your respondents and still have a 0.9 correlation with the true score. And it doesn't matter if you're losing the peripheral nodes, that would be the negative 0.7, or the positive nodes. So you can either remove the central nodes, hurt you more than the peripheral nodes, but by and large, you're going to do good in that set. So that's what these tables mean. The A's mean that you could lose up. It was unestimable in the sense that by the time we got to 70% missing, you were still not below 0.9. And so in co-authorship networks, you can lose a bunch of people and not hurt yourself, right, in these particular measures. Does that make sense? So so that's the whole point of these. You can go through, if you look at the overall across all networks, you have this ability to ask yourself, what happens when I'm missing data? For something like in degree, like on average, if you're missing 50% of the peripheral nodes, you're not going to hurt yourself much. If you're missing about 1/3 of the central nodes, you're still not going to hurt yourself. I mean, a correlation of 0.9 between the true and the observed is still really high, so that's a pretty high threshold. So we're happy with that. Closeness and betweenness centrality are the bad news stories. So in these cases, if you're losing, you can only lose about 17% of the peripheral nodes or about 10% of the central nodes and still get a reasonable, a high fidelity estimate of betweenness centrality. That's how you would read that sentence. And the same sort of stories then with these topology scores. And so what I hope that was the wrong button. So what I hope you do is go and check some of these tables out when you're thinking about your own data, and say, well, this is what, if I assume that I've lost the peripheral nodes, which is the negative score, or the central nodes, if it's the positive score, then you can go and look up and say, well, where am I in this set? How likely am I to be in trouble with the measures I'm reporting? Now the obvious question is, if I'm missing data, how do I fix it? And so it might be, all right, Moody, you've told me that I actually am going to be a little bit biased. So how about if I do the standard thing that we do in regular statistics and impute my missing data? We can impute it based on some kind of a set. And so the final paper in this series where we tried to introduce a series of corrective behaviors. And we do this in a series of different ways. We start with if this is your missing data in reality, so the true network is the union of all of these, but you're missing these two red nodes and thus all of their relations, what do you actually get, right? So how would you impute these data? So the standard thing we do in the social sciences is we just work with the data we have. And so we're calling this list-wise deletion, just because it's just like you would do in regression context where you toss out any cases where you have missing data. In a network standpoint, another option is to say, well, we know that these two nodes, for example, nominated somebody out in the network. They didn't reciprocate. So let's just go ahead and keep all the ties as reported by my actors and add back in the nodes that are missing. So in this case, we know that that node E was named by two of our respondents. We put the directed edges from A and D to that node, and we just keep the asymmetry in the network. The alternative is to say that we'll put them in the network, but we'll assume it's a reciprocal tie. And the advantage of doing that is that whenever you impute this way, where you just add the ties as observed, by virtue of the fact that E can't nominate anyone else, you can't get a closed circuit. So you have to have, in this case, there's no way, if you were to think about a flow process, for example, it would come here, it would start there, and it would always get stuck on these nodes that you've added. So in order to avoid that, and some of the circuit-based measures in the network are going to assume that you can move things around, you want to have a reciprocal tie so that any flow that comes here can find its way back to the people you sampled. So that's why we made that assumption. Both of those are hard rules. There are a series of probabilistic rules. And so the first rule is to say, let's just assume that we have some proportion of ties that are reciprocal. So we're going to apply that proportion, we're going to flip a coin with that weight and reciprocate the tie as observed. And the final approach is to say, well, we can do better than all of these heuristic rule of thumbs by using a statistical model of the network. And if we know homophily, we know transitive closure as the network as a whole, we can assume that's true for the unobserved networks, and we can impute ties based on a model. So that's the logic of these different pieces we've gone through and done. And so we do the same exact thing. In terms of the model set process, we have essentially a very simple version, which is just a dyadic independent model. We have a baseline probability of a tie forming at all, and then some homophily terms that are built into the model. And then we have that plus this transitive closure effect. And the same sort of kind of model that we go through, we do, the display got to be absolutely ridiculous. So we have a table in the paper that says, do this, right? So, which is I think what many sort of users want. So for example, if you're interested in calculating, total degree, and your network is directed, then quite honestly, you can do anything you want, you're going to be fine, right? That's the best choice. It's like there just is no difference in any of these responsibilities. If you, if you have any type of missing data, then any of the simple models are going to be just fine. You don't need anything harder than either the asymmetric set or the coin flip. If, on the other hand, you're interested in closeness centrality, then you probably do need to do some kind of a more model-based approach, right? Regardless of what kind of missing data you have. If you don't see your combination here, so for example, we don't have in degree with undirected, that doesn't make any sense, but the goal was to go through and figure this out. If you go through and you look, the thing that was probably most surprising to us, that's sort of the big picture take home here, is that the list-wise deletion strategy, and these are bias scores now on the y-axis as opposed to correlation, so it's a different metric than we had in the last set of slides. We got a different reviewer, so they wanted us to switch it up. So we ended up with, the basic story here is that you end up with doing list-wise deletion is probably the worst thing to do generally, because you're just throwing away so much more information. That across any of these kinds of scores, whether you're selecting peripheral nodes or central nodes or just missing data at random, in all cases, the list-wise deletion is going to lead to the most biased score. But the more surprising bit is the other kinds of the simple imputation methods, before you even get to these complex model-based things, tend to work just fine, right? So the model-based isn't that hard anymore. It's a lot easier to do now than when we wrote this paper, but it's still the case that it's a lot of extra sort of architecture on top of those kinds of models that you don't want to do unless you can help it. And often cases, you just don't need to for the things for the problems we want to answer. And that's also true. So that was for our undirected networks. It's a similar result for directed networks, and a similar result for for the different kinds of centrality scores. So again, throughout the cases, there are a couple of bits and pieces here where there's a slight advantage over one modeling strategy or another, but by and large, these things tend to work pretty well together. And again, there's these lookup tables in the model, and I'm not going to bore you any more than that. There's another thing that's in this paper, which is kind of cute, which I think is kind of fun, which is we added a series of decision trees. So if you want to go into the model, you can say, I have a centralized network. I'm interested in calculating centrality measures and their path-based measures. Then probably the best choice that you can do is a probabilistic imputation. If instead you have an interest in something like topology measures on undirected networks, then a complex model is what you're going to need. So these trees are in the paper if you want to go through and look at it. Now the reviewers rightly said, come on, Moody. No one goes to a hard copy of a journal and looks anything up anymore and traces through the back of a table. It's like, find something for us that people can do. Make us an app. So we did. We made an app. And so we made a little app, which is our network bias calculator. The problem is it was calculated in Java, and now no one likes Java anymore because it's a security risk. So so it's not working right now. It's died recently. So unless your administrators will let you use Java, in which case you can have it, but our administrators won't. So we don't have it. But we're rewriting it as a Shiny app, and so it'll be available, hopefully, knock on wood. This is one of the things, Emily doesn't know it yet, but this is one of the things she's working on this summer, is to translate this code into Shiny. And so in that case, then, what this allows you to do is to go in and pick one of these archetypical network types, plug in the kind of reason your data is missing, and some assumptions about what you have in your network, and it'll pop out this thing that tells this is the amount of expected bias you would expect in that kind of a network. So it's designed to be a tool to say, all right, and you might think this is a lot of work, and many times reviewers don't want this, but grant reviewers do. So when you're writing your NIH grant and you have this is the equivalent of a power calculation in a network study. You're going to say, well, we assume we're going to get an 80% response rate, and and if I'm a grumpy network reviewer, I'm going to say, well, that means all your scores are completely worthless. And you can say, no, they're not completely worthless. In fact, given some reasonable assumptions about the network, it looks like we're going to have a correlation of 0.9 in this case with this true scores, and it'll be perfectly valid. So it's a nice way to be able to answer those questions, which is why we built this thing. All right, I want to spend a little bit of time now giving you an overview of network models. And then I think by now the backup coffee should be done. And so, is it someone yes? It is done, right. So I will, so this will take me about, so I'll do this quickly so there's time to have some coffee before Craig comes up. But I just want to, again, this is maybe let me do it in 2 steps since these are really 2 problems. Are there questions on missing data? Questions, comments, thoughts, please? Yeah. We did not. So we did a centrality gradient for peripheral versus central. And so we had your missing data was either highly conditioned by your closeness centrality, either positive with a positive or negative slope. So that was what we did. We could instead say that males or whites or rich or poor are more or less likely. And so if those we haven't looked at that. So the question is if those things correlate with centrality, then you can sort of back out that set. If it's segmented, then it probably doesn't affect any of the rest of the network other than your ability to understand the segmentation. And so that's why we just didn't go that direction. But it's a great question. So if you want to move that way, we have the architecture set up. So, other questions, please.
I have a question about the homophily.
Mm-hmm.
So do you think the correlation of the homophily measures with missing and the true score will change when your actual homophily score is high or low?
We did both. So we induced the way we tested this is we induced homophily on the network with a weak correlation and with a very strong correlation. And in both cases, they were remarkably, if your data is missing at random, you're golden, nothing matters. If your data is missing based on peripheral versus central, there's a you're slightly more likely to get a bias, but even then, not much. So homophily scores, it's kind of remarkable that homophily scores are just remarkably robust to missing data. Unless, and this is the point that I think that might have been driven over here, we didn't test for direct selection on the dependent variable. So if you're looking at, say, smoking as your homophily score, and none of your smokers filled out your survey because they refused to talk to you, then you're certain to have bias, right? But so long as you're not selecting on the dependent variable you're trying to explain, our results suggest that it's really robust. Yeah. All right. So now what we're going to do is a little bit of an overview just to get you in the headspace of network models. And so network models are this sort of broad, what I'm just using as a broad class of ideas to think about when you're doing what all of us have to do to get a paper published. We have to collect some data, describe the data, model the data. And so the model of the data is usually a regression model. And there's about 3 or 4 different flavors of these models that are common in our field. By far, I think the most common network model is what I call a network metric model. And in that case, there's some dependent variable, self-rated health, smoking, the number of hours you exercise, and it's a function of a standard intercept, and you can make that random or whatever it is you like to do, some network score, and everything else you control for, right? And so there's probably 1,000 papers that look like this. And so the question is that kosher? Can you do that? And in most cases, you're doing a standard general linear model, right? And as such, all the standard assumptions about that error term, that little guy over here on the left, on the right, apply. And so what we assume is that you have homoscedastic, the assumption of regression is homoscedastic error terms that are not autocorrelated, right? So independent IID assumptions on this. The problem with a network model is that almost always that assumption is wrong, that the E's are going to be network, you're usually going to have at least network autocorrelation. And so network autocorrelation says that my error is correlated with the error of people I'm connected to. And so in practice, most people ignore that. So you will be like 90% of the papers you cite if you do nothing and just use the network score, run the model. That's what people typically do. And at first, I was really concerned with that. And so John and I spent a lot of time, and Jeff and I have a third sort of, another set of papers that we're starting on to try to really unpack this set. Because the right thing to do is to replace E there with a network autocorrelation term. So you have EIJ, which is going to then sort of give you a feedback process built into the model. And I'll show you what that model looks like in a second. But it turns out that if you have just error autocorrelation as opposed to behavior correlation, so if it's just that the errors in your model are correlated, then like a lot of autocorrelation, all it does is increase your standard errors. And so you end up with a less precise estimate, but not a biased estimate. And so for the vast majority of cases, you've already soaked up a lot of the variance in that autocorrelation with your centrality scores or your clustering scores or something like that, because it turns out that in most settings, people's centrality is highly correlated with their peers' centrality. So that means that I actually have an instrument for the network autocorrelation when I'm doing it. And so in practice, this ends up not being a bad estimate. It's usually pretty close to unbiased. And it's the one complication is that it ends up being a confounded interpretation. Is that what the centrality score means isn't just that I'm central, but that I'm central and I have peers that are like me. And you're not able, by virtue of just putting this in the model, to be able to disentangle what proportion of that is autocorrelation and what proportion of that is a pure centrality effect. So that's a short way of saying it works, right? You can do that. What I recommend doing is always adding some other features that are going to, one is to do the network autocorrelation model. It turns out that it's not that hard to do, and we'll show you that a little bit later today. But the other problem is if you just control for other connections in the network, you also do a good job of soaking up those kinds of problems. So if you have a community detection sort of piece, put that in as a control. If you have a latent space, put that in as a control. So you can put all these different features in the model, and that accounts for a lot of those kinds of errors that would otherwise be there. And so if I care about prominence, and I think that popular kids are more likely to smoke than unpopular kids, then I want to control for what clique they're in. So I want to have a control in the model for what community they're in and for the other things, and that ends up simplifying the model quite dramatically. So again, what's the best practice? You can do nothing. That's what most people do. It's hard for me to recommend that you do nothing when we know there's a problem, but in practice, that's what most people actually do. You can add the network autocorrelation term. That's the most direct correction for a likely problem. There are ways in which that can go wrong, but by and large, it ends up being pretty straightforward. And there are two nice tools for this. The key one is a spatial autocorrelation model. Like R has a nice spatial autocorrelation package. Stata and SAS also have great spatial autocorrelation projects. So these are pretty easy to correct for. You can, if you're really down in the weeds and you want to do this the hardcore way, you can just put the mean of your peers' dependent variable in there, and that'll soak up the vast majority of it. So there's lots of ways to correct for this that are reasonably simple, simple enough that it's probably worth doing. And you might learn something. All right. The second set of sort of broad class of models are what I refer to as dyadic relational models. In this case, to some dependent variable, what you really care about is the relational similarity. So are Craig and I similar on our opinions about the environment, right? That's the kind of question that we might ask. And it's a function of our being tied to each other. And so it's the network association, this AIJ, we think has some causal effect on our similarity. And we control for everything else in the network. The complication here is these are dyad models, and so you have all of the network autocorrelation that are built into the model that you have otherwise, but you also have repeated observations. And so you have these two sources of non-independence built into the model. The good news is that you know what's there, right? The theoretical advantages of these is that Craig and I's similarity might be different than my and my wife's similarity because we have a different relation, and so we have a different sort of outcome. And so it doesn't essentially take my outcomes and average it across all the nodes. You can do things that are directly relational. This is by far sort of the best practice for dealing with these things, particularly if you have ego network data, is multi-level models. So you can nest the relation inside the person, and by nesting people and persons, you correct for all these features. And this is what Bria Perry presents in the advanced version of the network. If you have both sides of the network, it gets a little more complicated. The thing to do are these things called cross-nested HLMs or dual random effects models, where you essentially put a random intercept. You treat this I should have written my equation better. You treat this intercept as, there's one version for I, one version for J, and that intercept then is a function of lots of other things. And so these models are estimable. They end up being a real pain in the ass to fit, just to be honest with you. So if you're going to do them, just give yourself a little bit of time because it's going to take a while for them to converge, and you're going to specify them in ways and it's not going to work, and it's going to make your life a little bit miserable, but they will typically work okay by the time you get them. You can also, I think, and again, I'm a big fan of as Peter Mucha likes to say, the simplest non-stupid thing. So what's the simplest non-stupid thing you can do? The simplest non-stupid thing you can do is include explicit controls for the similarity that would be otherwise confounding your estimate of the model. So the number of shared friends we have. So Craig and I's direct effect on each other is a function of the fact that we also jointly hang out with lots of other network people. So that's something that we can include in the model. Because the fundamental assumption of all of these general linear models is not that the cases are independent, but that the errors are conditionally independent. And so if you condition on all the right things, then the leftover unobserved error is unlikely to be that damaging. So that's all by way of saying is that when you try to do the right thing and it doesn't work, don't feel so bad when you do the reasonable thing that will work, right? And because at some point you have to finish a dissertation and get your papers published. So, get those things out there. The other thing to do is to not make these bad assumptions. And so you cannot make some of these bad assumptions by using non-parametric models. And so there's this whole series of non-parametric effects, such as QAP and multiple regression QAP, which don't make the same kind of inference assumptions that the general linear models do, that allow you then to sort of sidestep the problem by not making the assumption in the first place. And so that's a nice solution, but it requires a set of specifically known tools. And then finally, there's a series of, if depending on the way your question is structured, you can treat this as an edge level covariate in a predictor of another relational model. So if my question is, who hangs out with each other, it could be a function of who talks to each other. And so that's a bad example, but you have those kinds of, you can think of two relations in a multi-relational network with one predicting the other, and you can use those tools. Which then takes us to the final model, or final class of models that we want to talk about, which are these network prediction models. In this case, you have the adjacency matrix on the left-hand side of the equation. You're trying to figure out what predicts a tie between people, or the strength of a tie if it's a valued relation, as a function of some features in the network. And there's usually two classic types of features. There's some type of homophily feature, so same race, same sex, same education, what have you. Or there's some endogenous feature of the network itself, transitivity, reciprocity, something like that. So those are the kinds of things that matter. And you might have a bunch of other things, of course, in the network that could be there. But substantively, those are the features that are there. And those are what are known as exponential random graph models. And so we completely flip this around and we say there's this probability that the tie exists in the network as a function of a series of statistics on the graph. And it turns out that those statistics can be of two classes. They can be either dyadic independence, what are known as homophily effects, or they can be endogenous non-dyadic independent effects, which are there. And I'm going over this really like that. Those last two sentences were gibberish to half of you, because we're going to spend an hour and a half on it here in the afternoon talking through all of the details of that. So again, this is just I'm telling you things multiple times today because it's a lot. So there we are. Okay. So yeah, I did that. And the final, why is that? Oh yeah, I guess did I miss those? I should have had a 4. That makes more sense. All right. So the final set of models, I just talked about these. These are contagion models. So the final set of models are what Craig's going to help us think about more substantively, and actually are these things called peer influence models. A peer influence model says whatever my behavior is on the left-hand side is an endogenous function of the behaviors of my peers. And so how you estimate that, what that means sort of theoretically, is a good question. And we have to make sense of how that does it. But it turns out that estimating these models, there's now lots of tools to do it. And so the models have to make assumptions about convergence and about equilibrium and so forth. But in practice, there's lots of good ways to get this. If your data is dynamic, we have what are known as Siena models, or stochastic actor-oriented models. That should be an AOM, not an OAM. But these actor-oriented models are going to be the topic of discussion on Friday morning. So we'll go over those in great detail. One thing I'm just going to point out, and I should have put this on its own slide as opposed to at the bottom of this last slide, is that there's two different sorts of problems that come up in most of these models. There's an analysis, sort of an estimation problem, and there's an inference problem. So there's a question of, can I get the model to work, and what does the model mean? And those are two separate questions. And can I get the model to work as an estimation problem, or is my answer correct given the data that I have, is often the least problematic of your questions. The more problematic question is, what does it mean? Right? What's the theory that drives this? Is it selection versus influence? The coefficient is exactly right. If I'm trying to just predict the outcome, the model is going to be accurate. But interpreting what it means something else. Right? So that's not a problem we can fix in the machine. It's a problem you have to fix as analysts. Does that make sense? All right. I'm putting myself asleep. I don't want to take too much time with Craig's. The coffee is here. So let's take a get some coffee, say hello, and we'll start over again once people are caffeinated.